And yeah, let's get started. So I am going to go over the solution first for the Super Bowl uh, problem. Okay, so if you look at my screen share, you can just look at this code here. Okay, so I did uh, I actually didn't use unit find for this. I did use um, the other algorithm, the priority queue. Okay. Yeah, so first I need to come up with the score, right, for each pair for any two teams, for each pair of teams, uh, what the score that would be achieved would be if they were playing together. Okay, so you can sort it in a matrix, okay, and then afterwards, right, we do the maximal spanning tree in this case, right? So what I did is create a Boolean variable to say, okay, what nodes haven't been visited yet. Create a uh, distance array to denote the best known distance from the tree to any other node. Uh, and sort them based on the distance, right? So it will be in reverse order. So I do flip the uh, subtraction here so that it's sorted by reverse order. Okay, and then afterwards, we loop through 12 n times to put nodes into the MST. Okay, yeah, and then when we put the node in, we loop through all its neighbors and be like, hey, if that distance is actually uh, more optimal than the one that we have, and it's not in the minimum span tree yet. Right, reprioritize the node, right, and update the distance. Yeah, that's it. Okay. Questions on Super Bowl? All right. Um, yeah. So let's start today's lesson. I'm gonna take attendance real quick. So Chenjamin's here, Arthur is here. Who else? Arnav is here, Alexander is here, everybody else is not. Let me send quick reminder emails uh, to those people. Yeah, so today I want to uh, do one more lesson on dynamic programming. Um, yeah, our competition is going to be uh, next weekend. Okay, so starting on the 15th and going to 17th or 18th, it's on the website. I can almost guarantee you there's going to be a dynamic programming problem. It's a very recurrent topic in the gold level. So today I want to show you some harder dynamic programming problems to give you more practice. Okay, so the first one I want you to look at. Shoot, I forgot the name of it. Let me pull up my notes. Okay, yeah, it's called Bessie's Birthday Buffet. All right, so yeah, so I put a link here, and you guys can spend a few minutes to look at the problem text. Okay, so I'm gonna give that to you guys. Yep, let's read it together. Okay, are we good? Yeah, this problem is hard. It's combining a couple of techniques. So first, it is a graph problem in a sense, right? So there's n patches of grass, and um, each patch is connected with up to 10 neighbor patches via bidirectional graph paths, and it takes Betsy e units of energy to move between adjacent patches. Okay, uh, so that tells us that it is a unweighted graph. So unweighted, as in all edges have equal weights. Uh, right, one is not weighted more than any other. Uh, so basically, to go from one patch of grass to any other patch, right? We can figure out the energy expenditure by doing a breadth first search to find the shortest path, right, from any patch to any other patch, right? Now, normally with the weighted graph, you would need to use Dijkstra's shortest. I suppose keep spelling shortest wrong. Right, you need to use Dijkstra's to find the shortest path in any arbitrary graph. But it's an unweighted graph. That means all edges are equal. Then you can actually get away with using breadth search, right? Right. And It's been a while since we've done BFS, but just to refresh our memory, so we have nodes, right? And then, so we start with a node, right? And with breadth first search, what we do is we visit all the nodes uh, that's say like 1 degree away from our starting node, and then all the nodes that are 2 degrees away from the starting node, and all the nodes that are 3 degrees away from the starting nodes, on the nodes that are 4 degrees away, and so forth, right? So with breadth first search or graph algorithm, right? So the order in which we visit these nodes, assuming that the top node is the starting node, right, would be we start at that, right, and then we visit these guys, and we visit these guys, and if those guys have neighbors, then we visit those as well, right, and so forth. Okay. Uh, And why don't I come up with the BFS algorithm real quick in code as well. So first thing we need to do is actually think about how to represent a graph. Right, so there's adjacency matrix or adjacency list. There's only 1,000 nodes, and it does say each node has only up to 10 neighboring patches. So each node would have only 10 neighbors. So at most there's 10,000 edges. So it's actually not too bad to use an adjacency uh, list, right? Um, so yeah, you can do something like this. The graph, okay. Yeah, so graph of I denotes a list of neighbors of node I, right? And of course we assume nodes are labeled from 0 all the way to n minus 1. Yeah, so that's how we can represent a graph. Next, I guess what we can do is um, just write the BFS. Okay, so the breadth first search algorithm, it's going to take in the graph, and it can take in a starting node, which I'm calling S. And what I can make it return is, I guess, an array like this. Okay, uh, so the return array uh, denotes, so RET of I is going to denote the min number of edges between start node S and node I. Okay. Breadth search is comparably easier than Dijkstra's in other graph algorithms, but yeah, let me put in the code for it anyway. So first we need to uh, return an array, right? So I'm going to call this int array. I'm going to initialize this int array, and um, it's going to be of length n, right? Sorry, let me do this first. Okay. Uh, yeah, and this is going to be of new int n. So this is the array we're going to be returning. So we can fill the entire array, I guess, with like -1. Right, so when we do a breadth first search, we will eventually visit all the nodes that can be visited. But if for some reason there are nodes that's not connected, that's impossible to be visited from my starting node, I want a way to denote that. So I'm just going to initialize all of them to -1. So if by the end of the algorithm, the number the value is still -1, that means it's not reachable. Okay, seems reasonable, right? And then I'm going to do this mean distances of s equals 0 as well. Oh, actually, I need to comment what this does. So just in case uh, you um, you're confused about this, so min distance of I, right? Again, it denotes the min known distance between s and I. Minimum number of edges between s and I. All right, so that's the first thing we need. Second thing we should have, and to be honest, we can kind of encode this information in the min distance array as well, but I'm going to separate it into its own Boolean array, just to say visit of I denotes whether a node has been added to our queue to be visited. Actually, I think a more appropriate term for this would be queued. Okay. So that's the other data structure. And by default, when you create an array like that, all the values are false. The only thing I want to initialize that would be set to true is the starting node, because we do want to queue it. Yeah. So with breadth first search, what we do is we just line up for each node that we're putting in the queue. We line up all the neighbors that we haven't visited yet uh, in the queue as well, and just keep removing things in the queue. So remember with the queue, right? We traverse the items in the queue in the first come first serve order. Uh, yeah, so that's going to be okay. In Java, the modern way to do queues is actually using a deck. So it's going to be a deck of nodes. Nodes are represented by integers, so it's deck of integer. I'm going to call it queue equals new array deck. You can also use linked list, but an array deck is actually a bit faster. Okay, and of course, start by queuing the start node, right? And I'm going to say while queue.size is greater than 0. Yeah, uh, remove the queue. Remove the node from the queue, right? And then we want to loop through each of these neighbors, right? So I'm going to say for int neighbor in graph of node, right? So if we haven't visited the neighbor before, then, I called it queued, not visited, queued. Yeah, then go ahead and put the thing in the queue and mark is as queued, right? Yeah, so that's breadth first search. Oh, and I actually need to also update the min distances entry on this neighbor as well. So min distance of neighbors. So like this is the first time we're visiting it, and since we're doing it in the breadth first search order, um, we are guaranteed to visit it with the fewest number of edges. And so min distance to the neighbor is going to be min distance to the node that we're visiting in this iteration of the while loop plus 1. Yeah, and then afterwards we just do min distances, return that thing, right? So that's BFS. Yeah, and actually, you know what? We need to do. We need to technically going back to this musical problem. So we need this BFS, but technically we want to see, right, when we land on a patch, like which patch to go to next, and we have to do this uh, cost benefit analysis trade-off, right, to see like which node is not too far away to go to. So um, which means we actually need to fill out a cost function, a cost matrix, okay? And we can fill it out using breadth first search by literally breadth first searching um, by starting at each of the different possible nodes. Because based on the problem, it's actually for us possible for us to start at any node in the patch, right? Um, so actually, I'm going to create a 2D array called cost matrix. And this is going to be, so cost matrix of I and j denotes the cost to go from node I to node j. And we need to fill it out by actually calling BFS n times, right? Because you want to know the cost starting at node 0, right? Going to any other node, sorry, node 1 going to any other node, sorry, and node 2 going to any other node. So you actually need to loop n times to do the BFS. So how efficient is BFS actually? So right, this actually looks kind of scary, right? Is this going to be efficient enough? Actually, with BFS, you're guaranteed to visit a node just once, no more than once, and you're guaranteed to visit an edge no more than once. So the complexity, the time, the runtime of BFS is actually just big O of n plus m, where m is the total number of edges. Okay, so total number of edges in this case is 10,000. So it's actually not that bad, right? Yeah. But so we do BFS n times, so 1,000 times, and each time, right, the number of iterations is 10,000. So 10,000 times 1,000, that's 10 million. Uh, large, but not that large. We'll make it. So far, so good. Any questions on this so far? Okay. So next, let's see. Let's go ahead and talk about how to do the rest of the problem. So we need to do like a trade-off as to like, okay, you start at one node. We're not even sure like which node to start at first, right? So it says here, Bessie can choose to start grazing at any patch she wishes. Um, and once it stop grazing, once she's accumulated a maximum amount of energy. It does say there's a certain condition here, unfortunately, Bessie is a picky bovine, and once she eats grasses of certain quality, she will never eat grass at or below that quality level again. It does seem like this makes the problem a bit more complex, but it's actually a good thing, and I'll tell you why. Okay, so let's look at the sample inputs. Right, so here are the sample numbers. Let me just paste that uh, onto the pad. Okay, so how do we read these inputs? So the first number is N and then E. So N, the remaining N lines describe a patch of grass. So we have 5 nodes here. They contain 2 integers, Q and D, given the quality of each patch and its number of neighbors. The remaining D numbers on the line specify the neighbor. Okay, yeah, it's kind of hard to understand. So why don't we try to actually draw a graph? Okay, so I'm gonna use my terrible paint skills because so there are 5 nodes, right? So I'm gonna label these nodes 1, 2, 3, 4, 5. Right, so 1, 2, 3, 4, 5. And the quality of each node, let me label it as, hold on, I'm going to put this in my other monitor for now. I'm going to label each node's quality with a green piece of text. Okay, so this is node 1 has quality of 4, node 2 is quality of 1, 3 has 6, 4 has 5, and 5 has 2. Okay, and finally, I want to draw the edges. Okay, so node 1 has an edge to node 2. I'm going to mark it black. Okay, node 2 has 3 edges to node 1, to node 3, and to node 4. Node 3 has 2 edges, one to node 2, one to node 5. Node 4 has 2 edges, one to node 2, one to node 5, and node 5 has 2 edges, one to node 3, one to node 4. Okay, so yeah, that's the graph here for the sample with sample input. All right, so let's see. The constraint, so without the constraint, like we're not sure which, not only are we not sure which node to start, like we don't know which node to go to, and like technically, without the constraint that we have to visit them in order of increasing quality, then there's like, it's like 5 factorial way of visiting these nodes, uh, and of course if there are 1,000 nodes, that would be 1,000 factorial, which would be completely intractable. um, but we're supposed to visit these nodes. We must visit these nodes in increasing order of quality, right? So node 2 has to be first, right? So the order at which to visit the nodes. And this is assuming that we don't skip any nodes. So let's simplify it a little bit. Let's say we don't skip any nodes. We visit all of them in increasing order. We probably don't want to do that, but let's simplify it for now. Okay. So node 2 has to come first because it has a quality of 1, right? That's like the lowest quality. And then node 5 has to come next, right? Because it has a quality of 2. And then node 1 has to be next, and then node 4 has to be next, and then node 3 has to be next, right? So 2, 5, 1, 4, 3. That is the order in which we need to visit these nodes, assuming that we visit all of them. Now the next thing to worry about is, okay, what if we don't want to actually visit all of them, right? So for example, starting node 2, okay, that might look reasonable. And I go to node 5, okay, it takes me like 2 edges to go to node 5, and then it takes me like 3 edges to traverse to get to node 1. So I don't know, maybe if we skip like node 5, right, then that might actually be not a bad thing, right? Because afterwards, right, coming out of node 2, I just go on to node 1. I only traverse 1 edge, right? So that might be a good trade-off. But having this order, we have a sense of like this has to be ordering, and now we just have to decide whether to visit each node or not. Okay, because I know that if I were to no matter what the optimal path is, right? Uh, it has to be in this order. It's just that we might remove nodes here and there, right? So you can imagine that each node actually has like an on and off switch. You switch it on, then yes, that means we're going there. Off, that means we're not going there. So right, it has to be in this order, right? So now our goal is to try to figure out whether to flip the node on or off. On meaning we visit it, off meaning we don't visit it. Um, right. So how many different combinations are there of on and off? Well, unfortunately, it's 2 to the n combinations, and n is 1,000, right? So 2 to the 1,000 is still intractable, but trust me, it's actually better than n factorial. That's a lot worse. So we made it a little bit better, although not good enough, obviously. 2 to the power of n, um, not acceptable. Hmm. Yeah, what can we do next? Well, yeah, can we reduce this 2 to the power n thing? Actually, the answer is yes, right? Because we're learning about this technique, and I'll just tell you, right, that we can actually reduce it using dynamic programming. Yeah, so in general, if you see something that's seemingly combinatorial, and it obviously has to be much faster than combinatorial, try dynamic programming. Uh, with the right setup, a seemingly combinatorial problem can actually be done in polynomial time, so n or like n squared, n cubed maybe. Uh, um, and that happens a lot with dynamic programming. Okay, so how do we do dynamic programming on this? Uh, well, um, I can I can do this. I can create a DP array where I want to keep track of like an optimal, I guess, like for each of the nodes, right? It's hard to formulate that, but yeah, I think we can do it. So maybe dp of I denotes the optimal total quality um, by landing on node I. Actually, this looks a little bit confusing. Let me, so first of all, I'm going to do something a little bit strange here. I'm going to relabel these nodes to be 0, 1, 2, 3, 4. I know that I have to traverse through these nodes in this order. Okay, yeah, so, well, some of them I may or may not visit, but so let's say this is like the node ID. I'm going to create a alternate ID. Let me call it O of I, O for order. So for a given node I, right, so the 2, 5, 1, 4, 3, these nodes, I'm going to define O of I to be what order the node is if we are to visit it in the sorted ordering. So node 2 would have O, so O of 2 would be 0, O of 5 would be 1, O of I would be, O of 1 would be 2, O of 4 would be 3, O of 3 would be 4. Uh, and here I actually want to change this a little bit uh, to be this. Okay, so dp of I here denotes the optimal we get by landing on O of I. So this means I don't really care what I visit before. It's just that I have to land on O of I. Okay. Yeah. So let's write out the base case. dp of 0 would be the optimal we get by landing on the very first possible node, which in this case would be node 2, right? So node 2 has quantity of 1, right? Okay. Well, dp of 1. So dp of 1 is going to be, so we can choose whether or not to not use node 2, right? So first of all, uh, 1, right? So what is the node at which O of that number is equal to 1? So that's actually node 5, right? Uh, so this here means, okay, I can either choose not to start at node 2. I can either choose to start at node 2 and then go to node 5, or I can just start at node 5 directly. Like if I start at node 5, uh, I get a quality of 2. If I start at node 2 and then go to node 5, I have to traverse 2 edges, right? So it would be, I'll get a quantity 1 here and then quantity 2 here. So it'd be 2 plus 1, but minus the cost of traversing 2 edge. Cost of traversing 1 edge is 2 per the problem, right? E is 2. So it'll be 2 times 2. Yeah, so this calculation here is, right, the quality we get by going to node 2 and then node 5 minus the cost it takes to traverse starting from node 2 and then to node 5. Yeah, so that would be, so this would be 2. Okay, so dp of 1 is 2. Yeah, does that make sense? So here, dp of 2, so right, so it would be like the optimum we get by landing at node 1. Okay, so we have a choice of either just starting at node 1 straight up, or we can uh, have our path where, so we start at sorry, we have a path that lands on 5 and then goes to 1, right? So if it lands on 5, then it would have accumulated 2 units of uh, uh, 2 units of quantity so far, right? And then plus 4 here, right? From the 1, and then minus the 3 edges that we need to traverse to get to node 1, right? Yeah, or we can skip node 5 and then start node 2. So node 2 and then node 1, right? So the quantity that we get would be 1 plus 4 and then minus the traversal of one edge, right? So minus 2 times 1. Yeah, in this case, this will still be 4, right? Yeah. Yeah, so if I were to write this out, it would be dp of I equals max of um, the uh, what is it? So this is a bit hard to write. Uh, so let me define O prime of I to be inverse of O of I. So in other words, O prime of O of I is equal to I. Okay. So this would be the quality of I, quality of O prime of I, plus max on right, which node to go from to um, get to node I, right? So it would be dp of j uh, plus the cost to go from node j to node I. Sorry, minus the cost to go from node j to node I. So this is max over j from 0 to I minus 1, if that makes sense. And of course, if this number is negative, then we just be like, okay, screw this. Let's not start in any of these nodes. So technically, if I were to make it even more correct, it'll be max of 0 comma that thing. Right. And technically, it's cost of O prime of j to O prime of I. Yeesh. So that's the dynamic programming formula here. All right. Questions on this? Yeah, this is definitely one of the harder ones. It combines like several techniques here. We have to do the BFS thing first, right, and then do the dynamic programming. Uh, and right, the dynamic programming setup, right, is definitely not obvious at first.
How does this deal with multiple nodes of the same value?
Oh, yeah. Good question. So I guess like one thing you have to do, so I'm not gonna code it in here, is right, if the previous node actually has the same quantity. So it's going to be max over j from 0 to I, assuming quantity, sorry, if quantity at j is less than I, right? So that would be the whole thing. I don't feel like writing this whole thing up, but yeah, you do have to worry about that, I guess. But yeah, that actually doesn't change the setup of the problem. You just have to write an extra if statement in your loop in the dynamic programming. Good question though. All right, so we got about 20 more minutes. Let's look at one more non-obvious dynamic programming. And this one really stumped me. I really have to look at the solution to figure this out. But yeah, well, let's look at this together. Okay. Yep. So here is the link at the bottom of the pad. All right, how are we doing? Yeah, let's talk about this. So it's kind of like a 2048 knockoff. So here's the sample input. So it's basically just an array with one, 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 two, like this, right? So that's like the sample. So you start with an array like this. So the game here is you can combine two adjacent cells that have equal value into a new cell with one higher, right? So you can, for example, uh, combine these two, right, and then be like, and then transform this to 2, 1, 2. Okay, I guess here you can no longer um, do any combining, so you're done. But in this particular map, right, the optimal is actually don't do this. If you combine these two cells, you can actually do 1, 2, 2. Okay, and afterwards, see these two adjacent twos. We can actually combine those as well, and we form 1, comma 3. Right? Yeah. Right. So how do we do this? The order in which you combine them matters. So you, at least my first intuition, which didn't lead me anywhere, is it's almost like a graph search problem where like you have a bunch of numbers, right? And maybe you can say, uh, okay, maybe choose to combine like these first, right? Or that we can choose to combine like these first. I don't really know yet, uh, but like, uh, but like I can do both, right? So I can traverse down the path. It's like a graph search where like this is one node, right, representing a configuration of the map, right? And then here by combining these two, we traverse down, right, to the next state of the game. So like you can model like each possible board state as a node. Uh, Turns out to be fairly intractable. So uh, here's one thing we can do instead. And this, at least to me, really isn't obvious. Our goal is we want to collapse a range of numbers like down to, if we can get them all down to like one cell, that would be great, right? So uh, let's suppose like the board is like 3, 1, 1, 2. Okay, so we collapse these two cells, right, to make it become the 2, right, and then we collapse these two cells to make it become, actually it's still 3, right, um, to make it become this, right, and then can collapse these two to make it become just one cell that is a 4, right? So yeah, in general, like the more we collapse, uh, the better. Okay, and of course, like we don't really know whether we can do that or not, but we can try to build a table to count for that. Okay.
Do we want to focus on the lower numbers first? Because we know the like the lowest numbers in the like list or whatever we're storing them as is will be like what combines and everything else, and nothing can be like used to like merge two of those together in the future.
Yeah, I think that's a good insight. It's hard though, like when you have something like this, like where do you begin though? Like, uh, like I get what you're saying, but that said, like, there could be a lot of tiebreakers, right? So maybe I can do this first, or no, maybe I can do like that first. Um, yeah, yeah. But well, let's try this. So within a range of numbers, right? I don't know if I can collapse them even to down to like one number. Uh, but if I can, that would be great. Okay. So what I can do is I can define a range. So a range has like a beginning index and an end index. Okay. And I want to tend towards collapsing an entire range down to like one number, right? Um, and the bigger that number is, the better it is, I guess. So I'm gonna write this DP array here. So 2D array, and and yeah, I'm just gonna copy this from my notes because I really couldn't have come up with that. So DP of I and j denotes the best score that is obtainable by collapsing the numbers in the range array of I to array of j. All right, so let's start with that first. Yeah, and I guess the base case, right, for this would be if it's dp of 0, 0, then it would just be equal to array of 0, dp of 1, 1. So that means like the optimal number that I can collapse uh, the range of numbers from index 1 to index 1, uh, what would that optimal number be? Well, it would just be whatever is at array of 1, right? So actually, yeah, I should say like the base case would be like dp of I equals array of I for I from 0 to n minus 1, right? Yeah, of course. Oh, and here's the other thing. The range of numbers might not even necessarily be collapsible into one single number, right? So in the case where, let's say my range has numbers like 1 and 2 like this, right? Then it's impossible to collapse. So if it's a 1 and 1, right, we can actually collapse it into a 2. Or if it's like 1, 1, 2, like if the range is like this, we can collapse it to like a 3 even, right? We can collapse these two first, right? And then that becomes a 2, and then collapse that with the 2, that becomes a 3. But obviously, not all ranges are going to be collapsible, right? So if a range are like this, that is not collapsible. And we need to denote that, I guess. Uh, so let's denote that as like -1. So dp of I and j equals -1 if range of numbers from I to j is not collapsible into one number. Okay. Yeah. Right. So uh, next I want to say, okay, so what about the recursive case? dp of I and j. Hmm. So dp of I and j, like, can we even collapse this? Well, can we even collapse this range from I to j? That would only be possible if there exists an index k such that dp of I and k is equal to dp of kj, right? Yeah, what does this mean? This means that we can collapse the range from I to j, like half. So if we take like an index k, right, somewhere in between I and j, that means, right, that there is a portion, right, which we can collapse down to one number, and then the rest of it, actually this should be k plus 1, apologize, and the rest of it can also be collapsed into one number. And not only that, those two numbers happen to be the same, right? And I guess not only that, uh, that number has to be not equal to -1. Yeah, because otherwise this is not doable, right? So this is going to be max over k of dp of I and k plus 1 if this is true, right? Yeah. Okay, so um, how do you actually implement this? Yeah, this is tricky, especially the base case is like usually when we have like a 2D dynamic programming thing, like base case would be like dp of 0, 0, right? Uh, the base case here is not 0, so how do we loop through each cell here? Um, yeah, so maybe what we can do is we can loop on the length of the range, actually, right? So the length would be like this, right? And then we can define I, right? So we can do like for int I equals 0, I less than n, I plus plus. Yeah, and then int j would be like I plus length minus 1 technically, because the index j is actually inclusive. So this is how we can traverse through the indices I and j while uh, we apply the base case and then do the recursive case. Uh, yep, yeah, yeah. And again, this looks kind of weird, but we need to do this because the base case, it doesn't start at like 0, 0. It starts at like I, right? Uh, so J here, right? J actually starts at I as well, right? So if the length is 1 to begin with, then it's going to be I. Yep. So yeah, this means we'll fill out all the ranges that has just a length of 1, and all the ranges that have a length of 2, all the ranges that have a length of 3, all the ranges that have a length of 4, and so forth. Yep. And then that there's actually going to be uh, there's actually going to be an extra loop here as well. So it's going to be k equal to what is it? I think k uh, let's say j k plus plus. Yeah, something like that. Yeah. I'm not gonna fill the rest in, but yeah, it's gonna look something like this. It's this solution. Yep. Questions on this? Okay, we have let's see, how much time do we have left? We have 2 minutes left. I didn't prep for anything else. Let me see if there's anything interesting I can squeeze in the final 2 minutes. Let me look at my notes. Trying to look at any dynamic programming problem that we haven't seen before, or that I can explain in like 2 minutes. Um, well, how about this? I'm just gonna kind of make up a problem here. Uh, that is related to this. What if the collapsing? So right now the collapsing requires two numbers to combine into one, right? What if I change the rules a little bit so that collapsing requires three numbers, right? So let's say you have like 1, 1, 1, 2, 2, right? So what you would do is you would collapse these three, right? So that it becomes 2, 2, 2, and then um, 2, 2, 2, right? You can combine them and collapse again into just 1, 3. So how would this formula look? So I'm gonna go back and copy what we had from before, right? So again, dp of ij denotes the best score that is obtainable by collapsing the numbers in the range from I to j. Um, right, so the base case dp of I and I is array of I, right? So as here, we'll be looping just max over k um, and L as well, right? So it will be like dp of I and j, so I and k plus 1 if dp of I and k is equal to dp of k plus 1 with L, right? And then dp of L plus 1 all the way to all the way to j, right? is equal to this thing as well, and that this thing is not -1. Yep, so it'd be like a quadruple loop actually. Yeah. Okay, that's all I got. Let's have you guys do these two problems for homework, and I will see you all next week. Bye, everyone.